Okay, so the law of total probability. Law of total probability. Okay, and it's a very simple law. Its derivation is not going to be very hard, but it's so powerful. You really want to know this law. Okay? And in fact, it's sort of the basis of methods for computing probabilities, like a build-up method for probability, just like we had a build-up method for counting. Okay. Now let me just remind you what's the definition of a conditional probability. So P of A given B is equal to P of the probability of A and B, okay, divided by the probability of B. Okay. Now it's very useful sometimes to write this in another way. So this is, if and only, is equivalent to saying that the probability of A and B is equal to the probability of A given B, okay, times the probability of B. So all I did was rearrange this and multiply both sides by the probability of B. Okay, and okay, so here's just a review, a repetition of the definition of a conditional probability. Okay, now let's go back to the sample space. So we have the sample space, which is omega. Okay, so the set of all possible outcomes, and consider an event A. Okay, and we're interested in the probability of the event A. Okay, now suppose that there's another event B, and we've been talking about conditional probabilities and so on and so forth. So let's consider another event. So let's call this event A. Okay, and let's consider another event B. Okay, so this is another event B. Okay, so if this is the event B, then outside of this event B is the event B bar, the complement of B. Okay, and observe that the event B breaks up A into two regions. Okay, so I'm going to call the first region, I'm going to color the first region blue, and I'm going to color the second region red. Okay, and let's see if we can figure out what these two regions are. Well, this region here is easy. This is exactly A intersection B. Okay, no problem. That's the blue region. What about this region? Well, it's A intersected with what's outside B. So this is A intersection with what's outside B. Okay. Now, so the outcomes in A, so A is equal to A intersection B bar, A intersection B, union A intersection B bar. And you can see that these are two disjoint sets. So that the outcomes in A are those in A intersection B together with those in A intersection B bar. So we can compute the probability of A. It's a sum rule for disjoint unions that applies to probability, just like we had the sum rule for counting, for sizes of sets. Okay. So the probability of A sums the probabilities of all outcomes in A. So we can sum the probabilities of all the outcomes in A intersection B. Okay, and add that to the outcomes in A intersection B bar. Okay, so that's the sum rule. So we're just using the sum rule for adding probabilities. We add all the probabilities, or we can add it in two steps. Okay, and now I'm going to use this reformulation of conditional probability. So this guy here is the probability of A given B times the probability of B. So the probability of A intersection B is the probability of A given B times the probability of B, plus the probability of, so it's just A intersection B bar. I replace B by B bar. Probability of A given B bar, complement of B, times the probability of B bar. Okay. So I'm going to box both of these, because both of these are very important formulas. Okay. And basically, they allow us to compute the probability of A as a sum of two terms, either the probability of A and B plus the probability of A and B bar, or the probability of A given B weighted by probability of B, plus the probability of A given B bar weighted by the probability of B bar. You can think of this as a case-by-case analysis for probability. Okay, so it's kind of like a probabilistic case-by-case analysis. Okay. And what matters, so we consider the outcomes in A as two cases, those that are in B and those that are in B bar. You can consider more than two cases if you have, for example, a third case. You might have a third case. You can do this for more than two cases, and we might even see some examples of that. But for the moment, this is the fundamental law of total probability. Very powerful. Okay, so let me show you, some of the uses of this law of total probability. So, example. Now, I'm going to show you some examples where it just makes computing probabilities easier, but you can always resort to the outcome tree method. So you have a box with 3 coins. Okay, 2 are fair, that means they have a head and a tail, and 1 has both sides heads. Okay, so it's 2-headed. Okay, so it's extremely unfair. You flip it, you can only get heads. So you pick a coin at random. Okay, so you pick a coin at random. So let's start doing this experiment. You pick a coin at random. Okay, and you can either pick, so there are 3 coins. So you can pick the fair coin, fair 1, let's say. You can pick the second fair coin, fair 2, and you can pick the 2-headed coin. Okay, and you pick a coin at random. So each of these choices is equally likely. Okay. Then now you're going to flip the coin, and we're asking what are the chances that you get a heads. So you can flip the coin. If you flip the fair coin, you can either get heads or tails, half, half. Okay, if you flip the fair coin, you get heads or tails, half, half. But if you flip the 2-headed coin, you can only get heads. Okay, because it's 2-headed. So the chances are 1, probability 1 that you get heads. So what are the outcomes? In this case, the outcome is heads. In this case, tails, heads, tails, heads. And what are the probabilities? 1/6. Okay, 1/6. 1/6. 1/6. And 1/3. Okay. And so you picked a coin and flipped it. Okay. And, we can ask, what are the chances that you flipped a head? So what's the probability of heads for this experiment? Okay. Well, we need to identify the outcomes. 1, 2, 3 outcomes. And so the probability of heads is here are the 3 outcomes. Okay, so the probability of heads is 1/6 plus 1/6 plus 1/3, which is equal to 2/3. No surprise, because you have a 2-headed coin in there, there's some chance that you pick the 2-headed coin, so the chances of flipping a head are 2/3. Now let me show you how we can easily compute this number without all this sophistication of the outcome tree. The outcome tree always works. Okay, but we're going to try to compute it now using the law of total probability, just to illustrate the law of total probability. Okay, so using the law of total probability, we are interested in the probability of A, probability of heads. Okay, and we can consider 2 cases. So you can think of this as case-by-case analysis where you have 2 cases. Either B happens or B does not happen. So it's the probability of heads given what? Given that you picked a fair coin. Okay, but now you have to weight it by the probability of fair plus the probability of heads given that fair did not happen. So complement of fair. So if fair did not happen, it means you pick 2-headed times the probability of 2-headed. Okay, and now let's see if we can compute these things. Well, the probability that you pick a fair coin, since there are 2 coins out of 3 that are fair, this is 2/3. The probability of getting a head, if you have picked the fair coin, given the additional information that the coin is fair, well, this we know, this is 1/2. Okay, the probability of the 2-headed coin is 1/3, because it's 1 out of 3. One of the coins is 2-headed. And the probability of getting a heads, if you have the 2-headed coin, is just 1. So this is 1/2 times 2/3 plus 1 times 1/3, which is equal to 1/3 plus 1/3, which is equal to 2/3. Bam! Bam! Okay. So easy. No need of outcome tree, nothing. We're using the law of total probability. Okay. So, let me erase this example and come and show you something very interesting. Something very interesting. Now, by the way, there's lots of exercises in the book, lots more examples in the text. Okay, so work through the examples in the text and work through all the exercises and pop quizzes, because conditional probability is subtle, and being able to use the law of total probability efficiently and with ease is a very powerful asset. Okay, especially moving forward when you want to compute probabilities. Okay, so I'm going to come and show you something interesting.